Okay, now today we will have the second lectures by Alberto on the neutrino physics. Okay, Alberto.
Thank you, Govinda. Good morning, everyone. Well, today we are going to follow the index that we were discussing yesterday. And now we have the three-neutrino oscillation and the future in three-neutrino oscillation. Well, in this future, there is an experiment that writes in the future of three-neutrino oscillation, and this is the Dune experiment. Basically, Dune is a mu neutrino beam. It's a mu neutrino beam starting from Fermilab and reaching Sanford underground research facility after traveling 1,300 kilometers. The characteristic of Dune is that they have a wide band beam, what means that you have a wide band of energies, and it is very good in the sense that you can be able to be sensitive to the first oscillation maximum and the second oscillation maximum. Remember that I mentioned yesterday that we have this L over E, which is the basic experimental parameters that you have to take into account in order to be the sensitivity to oscillation. So also they can have separate neutrinos and antineutrino modes. And then what is the more details or further details is Sanford. Sanford is the home of Homestake. Homestake, remember that yesterday we were talking about the neutrino history and talk about the famous Homestake experiment. Well, Sanford was the location where was Homestake, and it is this is a depth of 1,478 meters. So what other characteristic of Dune is that they are going to have a tunable proton beam, with possibility to upgrade the power of the beam. No? Well, basically, Dune is 4 liquid argon time projection chambers of 17 kilotons. And something about, well, yesterday we heard from Elisabetta how it works a time projection chamber. So I am going to add, probably I'm going to repeat what she said. So basically we have the charged particles created from neutrino interaction that they can basically release its energy to ionizing or exciting argon atoms. And then from the ionization, the ionized electrons, they are going to be drifted. Well, this is very nice. They are going to be drifted and they are going to be captured in this anode wire plane. So with that information, you are going to be able to reconstruct the track and also to the calorimetry. Besides, well, from the excitation point of view, as Elisabetta mentioned yesterday, you are going to get the prompt scintillation photons, and these scintillation photons are going to give you the time to start the time the event starts. So combining both information, ionization and scintillation, you are going to be able to make the 3D imaging reconstruction of tracks and showers. So some critical features is ultra-high purity that you need. The liquid argon has to be with ultra-high purity and very well uniform and stable electric field that you have here. Besides, only to mention, you have the arrangements of these planes, like this, with the wires are like this, with 36 degrees separation. So how the event looks like. You have here the decay electron from muons. You have a muon minimum, a muon MIP, and this is new mu charge. By the way, sorry. How can I keep this more? And then lift high. No. Okay, here. Okay, thank you. Okay, thank you. So this is the display. This is where the muon was a clear track. You have new E charge, the typical fuzzy showers, and you have the neutral current from the decay of pi zero, which is important, as I mentioned yesterday, because one of the most important features of these TPCs for searching nu mu nu e is to have a very good separation between electrons and photons. So this is the case, since you can get this separation distance from the vertex that can be a hint to discriminate photons coming from pi zero decay from electron showers. So this is a level display not by Dium, it's by microboom. In fact, microboom is also a liquid argon TPC. We are going to talk a little bit about microboom more further ahead. It's freezing. No? Oh, thank you. Well, this is the physics of Dium. It's very interesting that you can see, as you can see, well, first of all, you have here, let's understand what we are seeing here. You have here the unoscillated spectrum. This is the unoscillated spectrum, the nu mu charge spectrum, and then overlapping or superimposed in this unoscillated spectrum, you have the neutrino oscillation, the probability nu mu nu e for these different parameters. Well, let's see. For instance, this green means when you have delta Cp minus pi over 2. Remember that the two remaining measurements that you are going to work in the future in neutrinos are delta Cp and the hierarchy of the masses. So in this case, you can see, for instance, this is corresponding to delta Cp minus pi over 2, and the blue one is the case of delta Cp plus pi over 2. So you can see clearly the big difference. So it's going to be very sensitive of that. Also, other very important point from the sensitivity point of view is that you are going to see that this spectrum just matches with the peak of the oscillation. So you are going to be very, very sensitive in terms of statistics to this kind of oscillation, because this coincidence is not a coincidence, of course, it's prepared for that, between the peak of the oscillating spectrum and the peak of the oscillation probabilities. Well, in summary, Dium is experiment which is very, very capable to have a high sensitivity to the Cp violation phase and the mass hierarchy at the same time. This is something that you can review later, but this is oscillation probability expressed in the different parameters at this length for nu mu nu e, and you are going to have here the mass hierarchy, the Cp evaluation, but this is something that you can review later. So this is an example from Monte Carlo, obviously, an example of oscillated energy spectrum, and this is for nu mu survival, anti nu mu nu e, anti nu mu e. So what is interesting to see here, for instance, is oscillation is working because you have here that peak coincides or matches with the dip in nu mu coincides with the peak in nu mu e. Why? Because unitarity, no? Because all the probabilities has to sum 1. So it's very nice to see that. Well, this is the same, but this is for antineutrinos. And now the Cp violation sensitivity. This is the significance. Pay attention on that. This is the significance here. And this is for two cases, for the case the normal hierarchy, and this is for inverted hierarchy, two different hypotheses for the hierarchy of the neutrino mass. And you can see clearly that, for instance, for the cases of maximal delta Cp, you are going to have sensitivities or significance beyond the 5 sigma significance, which is the stamp that we can say that we have a discovery. And here you have the variations of delta Cp and how is the significance is varying depending of this value of delta Cp. So the bands are the range values of variation of the allowed values for Theta-II-3. Is it that for new fit is a package that make all the combination of all data for 2016, but there is no very much variation right now. So this is for the match hierarchy is very, very impressive. For all the values of delta CP, you are going to have much more than that 5 signal significance for normal hierarchy and also for inverted hierarchy. So it's amazing how powerful is the sensitivity of Dune. So other experiment that I want to highlight is the TOCAI-2 hyper Kamiokande, which is an upgrade. Hyper Kamiokande is an upgrade of super Kamiokande, which implies a difference of 9 times of fiducial volume. This is what is planned for hyper Kamiokande, and basically the beam for T2 hyper K is off-axis neutrino flux. Remember that yesterday we were discussing about, or I mentioned something that off-axis and on-axis. In this case, it's off-axis. So, for instance, you have here this is similar than that we have seen before for Dune at the beginning of the presentation. You have here that an off-axis nu flux and unoscillated. And you have here, for instance, the nu mu and how it matches perfectly with the peak of the new charge flux. This is the same for nu mu nu e, so it's very good, and of course it should be very good because it's prepared off axis. So here they are going to have similar results, or very, very similar results than Dune in that aspect, distinguishing the value of the CP violation, the mass hierarchy. So it's very good, it's very powerful experiment. And now we are done for the future regarding long baselines experiment. Now we are going to a step further. We follow in the path of neutrino oscillation, but we are going to talk now about the sterile neutrino, which is a very interesting anomaly happen in neutrino oscillation. Well, let's talk about it. Well, what is a sterile neutrino? It's a neutrino which does not interact with any boson W or C, that does suffer standard model interaction. This is the definition of a sterile neutrino. It's a right-handed singlet. This is a sterile neutrino. And you, for instance, if you add one sterile neutrino in your model, you are going to extend the neutrino mixing matrix. Remember that yesterday I showed you the neutrino mixing matrix 3 times 3, but you can enlarge the dimension to 4 times 4. This is basically the change that you have to do in order to enlarge your sector. So now, by the way, we are going to see in a moment, but the introduction of the sterile neutrino is due to some experimental data. So it's not an appearance not motivated. It has a motivation, experimental data that I am going to show in a moment. But this experimental data, I have to talk about that a little bit before presenting the full data. This is compatible with L over E. This is a hint or evidence of sterile neutrino, but L over E in order 1. What means that you have an experiment that in L over E in order 1 gets some signal from neutrino oscillation. What does it mean? It means that the delta M squared is in an order of 1 electron volt square, which is very different from the solar scale and the atmospheric scale. Only remind you the solar scale is 10 to minus 5 electron volt square, and the atmospheric scale is 10 to minus 3 electron volt square. So this is another scale, it's another very different scale that is in the context of this 3+1 neutrino oscillation framework. This is motivated by experimental data. So if you write down your equations, they're going very, very nice because you are going to have a very compact equations in the sense that for this case, for this L over E, if you evaluate your expression, this delta-3-1 and delta-2-1, which are the solar and atmospheric scale, are gone, are negligible. So in principle, your equations are going to be reduced when you have 3+1 at the expression, the two neutrino oscillation, which is very nice. I mean, very nice, very manageable. No? So this is the structure, and they are going to be dependent on delta square for 1. So 4 is motivated by the inclusion of the sterile neutrino. And this is are going to be the expression that you are going to manage in order to feed the data coming from this sterile neutrino experiment. So, well, what is the experiment that motivates the introduction of the sterile neutrino? Is this one. It's LSND, the famous LSND, the liquid scintillator neutrino detector. Well, the structure, how is the production, is pretty much the same that we are talking about, the beam. And you have, well, the difference that you have here, a beam stop that force the pion to decay at rest. So in principle, from that, you are going to be able to have the possibility of this antineutrino oscillate to electron antineutrino. So the detection is very similar in the case of reactors. You are going to have type IBD reaction, and you are going to have the two signals, the two delay coincident signals, with the difference that you are going to have here also a signal for the positron, a sharing on flight for the positron before he annihilates in matter. So in principle, this is the structure of the type of the signal. Well, again, when reinforcing that what I said before, the L over E is in order 1. This experiment was designed in L over E in order 1. And what was the experiment discovered was an excess in electron antineutrinos. Not expected, of course. So it was explained using the proposal of a new neutrino, which has to be sterile, because remember yesterday we discussed that we have only 3 active neutrinos. This has been very well measured. So the extra sterile neutrino that you have to add has to be sterile. So this was explained by this hypothesis. And here, this is something that appears continuously in a neutrino experiment. This is one in any experiment. In reality, this is an allowed region. No? It's only that some regions that we are going to see every moment. So this is an allowed region, the solution regions that you are going to get the data. The data fits with this solution region. So here again, well, this is the delta m square is greater than 0.02 electron volt square. And what was the problem was the persons obviously tried to explain what happened or try to confirm the signal. And in this, confirm or refute the evidence. And with that purpose was build this experiment, a minimum, which of course was in the same range of L over E to test this delta m square. And the production of the neutrinos is pretty much the same. This is in the booster neutrino beam, is in Fermilab, so the idea is the same that we have seen before. And this is a Cherenkov detector, the typical signature that we have already discussed yesterday. And then what happened, what at the end this experiment found, you are going to get the minimum confirms LSND and not refute, and obtain a low energy excess. And if they combine the neutrino and the neutrino mode, this low energy excess was consistent with 4.8 sigma overall significance. So the combination of neutrino plus antineutrino mode combined are consistent with LSND. And besides, an important point is what is the problem with this experiment, or what was the critics that you can do to this experiment is that they are not able to have a good separation between electrons and photons, which coming from this type of background, for instance. So from pi 0 and 4 deltas. So this problem, the problem that you expected to solve or eliminate is still, and you need to see what happened now. So we need to create other experiment that try to confirm or refute minimum. So this other experiment is microboom. And microboom is just an experiment consisting a time projection chamber. So the same principle that we discussed at the beginning. This experiment, just for the reason to use this time project, the TPC is able to have a very good separation between electrons and photons. So because has the requirement to do that, because it's a liquid argon TPC. So what happened with microboom, this is the latest result, is that you have to see this red line. Microboom has obtained an exclusion limit. In this case, the data of microboom indicates that there are consistency between the three-neutrino hypothesis and its data. But they have an exclusion limit, but this exclusion limit works from here to here, but not in this region. So still there are some portion of the region which is still allowed. So the problem is not totally solved, it's unsolved, it's still unsolved. And then let's go to another problem related with evidence, indicating the evidence of stellar neutrino. This other problem is the so-called gallium anomaly. So the solar neutrino experiments, like gallium, in order to make calibrations, they use a very intense radioactive sources. What is the purpose of using very intense radioactive sources? Is in order to create artificially neutrino electrons to make all the process that they do with solar neutrinos and to see and make calibrations. So they perform this task with different sources. Using these different sources, they obtain well, they use for chromium and argon, and they combining all its measurements, they found an inconsistency between the observed neutrinos respect to the predicted neutrinos. So in principle, this is the number of the average of all the data. So in principle, what happened here? Well, we have a deficit, a 2.9 sigma deficit. How can we explain the deficit? With stellar neutrino, with a hypothesis of stellar neutrino. And this is the region, the allowed region that covers the solution using stellar neutrino for gallium experiment. Then came to the rescue, in order to solve the problem, was prepared other experiment in Russia, which is called BESS, to test just this gallium anomaly, made obviously the similar procedure in order to test other experiment, but the idea is to test the same technique that they use. And what they found, 4 sigma deficit. So what is the status of the problem now? Unsolved. So in principle, we have still the evidence of gallium anomaly is still unsolved or still survive, whatever you want to see, whatever you want to say. Then here the region, there another anomaly which is different. We have first of all we have seen the LSND anomaly. Then we have seen gallium anomaly, and there is another anomaly. Please take into account that there are different anomalies. They are different anomalies. The other anomaly is the reactor antineutrino anomaly, and this anomaly came up when a group of physicists, two different group of physicists, made recalculations of the reactor antineutrino fluxes. And when they made these recalculations and recalculate the corresponding rates, they obtained a deficit in that rates, a 5.7% deficit in the average rate of reactor experiments. So they recalculate, first of all, the theoretical reactor antineutrino flux. They introduce this information and recalculate the rates of reactors, and they obtain a deficit. So the data points are here, and this is the probability considering the 3+1 neutrino scheme. And we can see again that we can explain this deficit using this hypothesis of stellar neutrino. This is the other anomaly related to stellar neutrino. the reactor antineutrino anomaly. Here the allow region, the allow parameter region, and then, sorry. Then again, we physicists design other experiments to test this anomaly, the reactor antineutrino anomaly. There are a bunch of experiments. We are going to mention only the general characteristics. And we have this experiment has the distance to the reactor core is very close. The idea, of course, is to test the reactor antineutrino anomaly. They have large background, and the signal background ratio is high, and well, this is also an extended core. So there is all these bunch of experiments that try to test this reactor antineutrino anomaly. And what is the status of that? The recent status of that is that we are going to get one of them, Neutrino 4, capture these kind of oscillations, and in fact is consistent with a stereo neutrino oscillation. Not reject the reactor neutrino anomaly, instead he get a solution using the reactor neutrino anomaly, or using, sorry, the stereo neutrino hypothesis. Then what happened with the others? In this case, there are contradictory results, because the others have obtained, all the other has exclusion curve. Yes, this exclusion plot are excluding, this is the solution due to the reactor antineutrino anomaly. Instead, in fact, this is a combination of the reactor antineutrino anomaly with gallium anomaly. And we have seen in the tree plot that big part of this reactor antineutrino anomaly is excluded. So in principle, there are a contradiction in these results between Neutrino 4 and the other very short baseline experiments. So now we've finished with these neutrino stereo anomalies, and we go to the absolute neutrino mass measurements. So let's go here. Well, the mass of the neutrinos should be less than 1 eV, or in order eV. So this plot here is very interesting, because if you think from neutrino oscillation, you get the delta m square difference, but you don't get the absolute mass. But from the delta m square difference, you can, from only using one mass, you can obtain the other ones. So this is that you are seeing here. You have the plot or the display of different curves of the M2, which is a function of M1 plus delta m square solar, M3, M1 plus delta m square atmospheric, and you display that. So what is interesting from this plot is the following, that there is a region, if the mass of neutrino is higher some value, that all the masses are quasi-degenerated. So you can differentiate between any mass. And there are other regions, obviously for lower neutrino masses, that you are going to be able to see that they are going to be effect of the hierarchy. So this is we learned that from this plot. And now, well, how do we measure the neutrino mass, the absolute neutrino mass? What is the way to measure the absolute neutrino mass? And this is through the electron spectrum from beta decay. But it's not the whole spectrum. You have to see here at the endpoint. Because if you have a neutrino mass, non-zero neutrino mass, you are going to get a shift or displace of this of the usual, assuming mass neutrino mass 0, displace of this endpoint shifted by the value of the neutrino mass, of the effective neutrino mass, by the way. So here is a plot of, in other words, we have here the electron spectrum, and we are going to look here. We have to look here at the endpoint. What is the big problem, of course, is that you are going to get a very, very small number or fraction of the decays are going to be located in this point. So the point is, or the idea is how we maximize this disadvantage situation. And then we use the nuclei that is usually used is the tritium. So the tritium, what is the advantage that has the tritium is that has the lowest Q beta. Q beta is the endpoint, is similar at the endpoint is 0. And this fact that has the lowest E0 implies that this fraction is going to be relatively high respect to the others possibility. Why? Because this fraction, the fraction of the decays at the endpoint are proportional to 1 over q beta to 3. So this is one advantage. The other is the high activity. Finally, the hydrogen isotope and its daughters are not complete structure, so theoretically can be calculated relatively simple. The calculations are relatively simple. So when you talk about the direct neutrino mass measurement, you have to talk about this experiment, which is scattering. So basically, it's experiment which try to isolate this decays in this endpoint region. This is the main objectives of this change is try to capture or isolate the electrons coming from this endpoint region. So basically, well, we have here tritium. At the starting point, you have 10 to 11 electrons per second. And after passing through all this stage, you are going to have finally 1 electron per second. And this is basically a filter of energies, because you are going to filter energies up to an energy very close to the endpoint. In this aspect, you have to comment about the main spectrometer that have here, which make the very important job, I mean the crucial job for doing that, for make this selection. And this is something called MAC filter. It's magnetic adiabatic collimation plus electrostatic filter. And basically, you have very intense magnetic field here, very intense magnetic field here. And these magnetic field are going to be diminished in this point. And also you have electrode that create an electrostatic field that is going to be the barrier for selecting these neutrinos. Only are going to go through the barrier electrons that have energy higher than the value of this energy. So basically, you the electrostatic filter integrates all the neutrinos above this energy. So one important point is what happened when the momentum transfers to the magnetic field is that this suffer a so-called adiabatic transformation, because if you can see, you are going to have here cyclotron motion, but as long as the B diminish, since the magnetic orbital moment of these orbits are constant, they are going to reduce the P transverse. So when they reach this part, the electrons are going to have almost fully longitudinal momentum. So what is the results coming from scattering? So basically, this is a region. This is the region near the point. This is a region for EV before the point, collected by scattering in 2 different campaigns, as they said. What is the result of scattering is bad news. They have an upper limit. They did not find any evidence of, I mean, not evidence, any measurements of the direct mass of neutrinos. Instead, they have an upper limit. And it's very interesting to remark how precise is this measurement, because if you you can see here, this is older experiment, and here this is the new ones, and here in this part are scattering. So it's practically impossible to notice the error bar. So here is assumed, so it's a very good, well, they make the fit of the mass, and this is of course consistent with 0, no, and even negative mass. So they have set this upper limit, which is the best at the moment for neutrino experiments. Well, this is the actual results, and there are a promising technique in the future, which is called cyclotron radiation emission spectroscopy. The idea basically is to trap these tritium atoms in a magnetic field. The decay electrons are going to be trapped in this magnetic field, but are going to doing this cyclotron motion. From that cyclotron motion, The idea is to measure this cyclotron frequency. If you are able to measure the cyclotron frequency, you can get the energy of neutrino due to these relations. And so in principle, it should be very exact. If you are able to capture the cyclotron motion or the cyclotron frequency, you are going to be able to get the electron energy in a very accurate manner. So they have proof the concept. Here is the proof of the concept, which is the phase 1 of project 8, as they said. And here is like how this kind of results looks like. You have this kind of straight lines, these slopes. And as I mentioned before, or let's see again, higher frequencies implies lower energies. So for these lower frequencies implies the higher energies. So in principle, this in these straight lines, you are going to have losses that are continuous, that an orbit that is continuously losing due to radiation energy. This is going to be a steady case, as they said here. And suddenly you have these jumps, and these jumps is due to the collision of these electrons with the gas, and they are going to jump to another, because I'm going to change abruptly the energy, and you are going to get other straight line, and this is the logic of this. But from this, you, in principle, you will be able to, if you match this with this frequency, you must be able to get the energy of the electrons. So they use electrons from internal conversion, this from krypton, and they capture this a couple of lines, TeV lines. So there is a very promising technique. They have worked in the phase 2 of this kind of experiment, which is using tritium. And they have obtained a similar spectrogram. They have extract a continuous tritium beta spectrum, but this is prototyping phase, of course. And they have obtained this kind of limit that is a level of prototyping. The target sensitivity is 0.04. The target sensitivity for scattering, forget the upper limit, but they have a target sensitivity of 0.2 electron volts. So this is more or less 1 order of magnitude better than scattering. So let's go to the nature of massive neutrino. We are going to switch. We are going to talk about neutrino mass, but we are going to other part of the other side of the big questions in neutrino. And one of the big questions in neutrino is, what is the nature of neutrino? So in principle, to understand what is the direction of the idea, or what is the idea behind of all of this, you have to remind that the difference between the lowest mass of the masses, the electron with lowest mass, which is the electron, with the neutrinos is in order to 10 to 6. So this means that the Yukawa coupling, if you consider the Higgs mechanism, the Yukawa coupling for electrons is going to be 10 to 6 orders greater in magnitude than the Yukawa coupling for neutrino. This is something that the physicists by a theoretician, because this is something that looks unnatural. So the idea is to expect that this Yukawa coupling constant should be more or less in similar order, but this high discrepancy in order take the attention of the physicists and worry the physicists, and they try to explain. There have to be a way to explain this kind of suppression of the Yukawa coupling corresponding to neutrinos. So for that purpose appears Majorana, which proposed a very interesting idea, which is the same with the following. He proposed that the neutrino and antineutrino are the same. They are not different. So with this proposal, you are able to propose a mass generation mechanism that can explain you why you have a very suppressed Yukawa coupling constants, or why you have a very suppressed neutrino mass. So this is the idea. So this nature of neutrino, Dirac or Majorana is related with the generation of neutrino mass. So let's go. Well, how we can test the nature of the neutrinos through double beta decay. I am going to be more specific in a minute. So double beta decay is when we have two electrons, but in principle, you expect also two neutrinos. So this process happens in the standard model, and this process in the standard model conserves the leptonic number. This is conserved. But if you have the possibility that the neutrino was its own antiparticle, was the same, the neutrino was the same. So in other words, if you had the Majorana condition, you are going to get the possibility to have this intermediate line, and this intermediate line gives you a sort of different double beta decay because it's a neutrino-less double beta decay. So you can see here, well, you have here emitting an antineutrino, and this antineutrino has to be absorbed as a neutrino. So in that point, the idea is that neutrino and antineutrino has to be the same in order to accept the validity of this diagram. So delta L, also the variation of the leptonic number is equal to. So, well, what is the strategy? What is the strategy is to look for a nuclei that will be able to decay only to double beta decay. So the idea is not to look like for all kind of nuclei that can decay through beta decay and through double beta decay. No. The idea is to try to select only the nuclei that can decay through double beta decay. And this can be done because you have some nuclei that have forbidden, that are stable against the beta decay, but they can decay through double beta decay. So this kind of nuclei you have to select for your experiment. So this is how it looks like the difference between the two neutrino double beta decay and zero neutrino beta decay, assuming different rates. But this is assuming because you don't know the rates, the difference between rates. When you have, well, you have of course upper limits, but in principle this is variable. No? So for that reason, you can see here that you expect that when you have two electrons at the final state and no neutrinos, you expect a monoenergetic because this is the sum of the energies for both electrons. You expect a monoenergetic peak. Of course, but it's going to be smeared by the detector resolution. But what is interesting is the dimension. For instance, if you consider that the decay rates are in relation 10⁻², this is, for instance, how it's going to look like, and this is 10⁶. Well, this is to get a flavor about how is the spectrum, what is the details behind. What is, for instance, that it's going to be some monoenergetic with the smear of the detector resolution. So the highlight of the neutrino-less double beta decay is given by this expression, which depends on the phase space factor, the nuclear matrix elements, and the so-called defective Majorana neutrino mass. This is different. You have to pay attention that this is different than the effective mass that I use in the part of the endpoint searches. So it's different. The mathematically, like the expression is different. So in this case, this expression can be affected if you have complex phases. And if the Majorana, if the neutrinos are Majorana, the UPMNS, the mixing matrix that I showed you yesterday, are going to be altered. I mean, you will have to multiply by other matrix which contain these Majorana phases. So this is how it looks like the effective mass with some values. And you are going to have this splitting due to the different phases that you can choose. Now we are going to see, well, what is the experimental requirements for these searches. And you can extract these formulas. It's a very interesting exercise. This is for the signal, and this is for the background. But what is the key factors here that you have to see is, for instance, the signal. The signal is proportional to the mass of the detector and the measure time. This is going to be exposure. The M times T is going to be exposure time. Is going to be very important parameter when you talk about this kind of experiment. Also, well, you can calculate the sensitivity for non-zero background and for zero background. Zero is for this case. So combining this and using this, the classical expression for calculating the sigma significance, you can obtain this relationship for the mass, the sensitivity for the mass, and the sensitivity for the high life. So ideally, if we look at these parameters, ideally you need a large detector mass, high isotopic abundance of the isotope that you want to use for neutrino less double beta decay, low background at good energy resolution for instance, for resolving the peaks. No? Remember that you have the two double beta decay that can be confused with the neutrino less double beta decay. So this is an example, the candidate nuclei, and you have, not example, this is a table of candidate nuclei. You have here the Q beta beta, and the high Q beta beta helps you to mitigate the radiation from the background from natural radiation. Well, you have low natural abundances, which is a problem, and this is related with the cost at the end, and also the phase space factor. This is general information for you to have a perspective of these values. So the backgrounds come from natural radioactivity. So from thallium and from bismuth, thallium you have a gamma ray line, and from bismuth you have a beta electron. And the other background is the cosmic ray muons that can produce cosmogenic radioisotope and long-lived radioisotope and secondary neutrons, and also fast neutrons and everything. So this is the backgrounds in general, and this is the classification by experimental technique. Bolometers, semiconductors, scintillators, time projection chamber, trunking calorimeter is not exhaustive list of experiments. I am going to talk only about a couple of them. And well, yesterday Elisabetta talked about the bolometer, so the idea I am going to give a few words. So the idea is you have a particle deposit energy, and this energy is going to be translated in a change on temperature. This change on temperature is that you are going to measure. And this is the basic idea of the bolometer. So what is the disadvantage? Oh, sorry, is that you have in this scheme you are measuring the total energy deposit, and you don't have information about the particle ID or external gamma rays coming from backgrounds. So this is Quore, is an experiment that uses this kind of technique. Is using tellurium, which has high abundance, and this is an array of tellurium oxide of 88 tellurium oxide correspond at 288.8 kilograms years exposure. Other experiment is HERDA, we use germanium detector arrays. And this experiment, well, the exposure is a little bit less than the exposure of Quore. Exposure, remember, is kilograms per year. And they are using germanium, solar nuclei. And well, something that is interesting to see, well, is how they do the elimination of background. And we have the muon veto. Here they have optical fiber and scintillators surrounding the detector. And besides, also have multiplier, photomultiplier here outside. And the combination of signal from the liquid argon, the light in the liquid argon generated in the light captured by these optical fibers, and these photomultipliers can give you a discriminator for muons, and well, the same for the argons that are decaying within the liquid argon, high isotopes of argon that can capture here, and also well the interesting point that I have to mention is that neutrino less double beta decay should be in a very reduced volume, should be decay in a very reduced volume. So when they have multi-site signatures, they have to reject that. This is a way to reject that this is not event related with neutrino-less double beta decay. Well, here we'll highlight the actual upper limit. The best upper limit comes from Kaplan-Sen, which is 2.3 10 to 26 is the best one that we have available at the moment, the best upper limit that we have for neutrino-less double beta decay. And then there are several projects in the future, but I am going to talk only a little bit about one of them, which is Next. Next has a large program that has several stages. So I am going to talk the first stage that they have proved the concept of how it's going to work. This is going to work with the TPC. The idea is to have a TPC. And the signature that they expect to see is something like this, where you have event, for instance, with one blob or two blobs. What is the event the type of event corresponding to neutrino-less double beta decay is when you have two blobs. When you have only one blob, this is discarded as event corresponding to neutrino beta decay, neutrino-less double beta decay, because this is the two electron event candidate. So here the program continues, and now they have this program Next 100, and this is going to be a 100 kilogram, okay, 100 kilogram mass scale. And let's talk about here. I am going to jump to this next bolt, which is very interesting, because they have the idea. This is supposedly this is an idea that was proposed in the past, but they now have the way to implement the idea to detect the daughter of the decay of xenon, which is very interesting. They are going to capture not only the signature of the two electrons, but also the daughter coming from the decay of xenon. How? They have developed a molecule, which is a single molecule fluorescence, that this molecule can bind with barium-2. And from this, they are working with two options. One is the bicolor mode, that you are going to identify the barium binded to a molecule when you have a different color. This is without barium, this is with barium. And other is off-on, that the molecule works like a switch. So the molecule regularly doesn't emit fluorescent light, but when binds with the barium, they emit fluorescent light. So this is the two techniques that they are deciding how is the technique is optimal for using in the future, but it's very interesting to mention. So the sensitivity are going to be very, very, very powerful. Now I am going to be a little bit faster, but this is a plot that you have to revise very carefully. Now I am going to mention very briefly, but this is the landscape of the neutrino-less double beta decay, considering the experiments, the current results, and also the future experiments. So you are coming from low detector mass to high detector mass, and the sensitivity is, if you go in this direction, the sensitivity is increasing. So why? Because in this axis you have sensitivity to the background zone. So if you diminish background and you increase the exposure, which is MT, you are going to get a better sensitivity if you go in this direction, doing that what I am saying. So I have a few minutes, so I am going to talk very quickly. Well, this is a very interesting part of the neutrinos, is that you also have astrophysical neutrinos. And they also have measures, they have data about astrophysical neutrinos. So I am talking about astrophysical neutrinos coming from extragalactic sources, not galactic sources, which is it's pretty amazing. So in principle, there is the idea that nearby to AGN nuclei, AGN is an active galactic nuclei, there is the idea that you can produce nearby that hole, you are going to be able to produce protons, and these protons, electrons, synchrotron radiation, and combining these effects, you, for instance, you are going to have proton interacting with the synchrotron photon, and from that you are going to get delta plus, and from that you get pion plus or pi zero. From also you can have proton against proton. In other words, you don't know what is this is a possibility that you are proposing in order to see that there is possible that you can produce neutrino from an extragalactic source. And this is the possibility that currently are discussing. So here from this pi plus, you are going to get neutrinos. So in principle, it's pretty amazing. Why? Because from very far distance, the neutrinos interact very quickly. So you are going to be able to capture if you have all the capacity for doing that, no? Of course. So what is the one important parameter that you talk about when you discuss about these astrophysical neutrinos is the flavor composition, the flavor neutrino composition, which depends of the production, of how is the production of these neutrinos. That can be 1 to 0, or 0, 1, 0, or 1, 0, 0. This depends on the physics that you are considering in the source. So this is an important measurement is to identify the different fluxes or type of fluxes of this flavor of fluxes, the flavor fluxes, and measure and make this comparison in order to disentangle which is the way that they are being producing in the source. So this is ice cube. So it's a water Cherenkov detector. You have these lines which contains all these strings which contains all the PMTs. And well, this is a type of event in ice cube. Here, the size of the field is reflecting the light collected because it's a Cherenkov light. This is the time. And this is how the event looks like. The big problem with ice cube is that you cannot distinguish neutral current, or it's very difficult to distinguish neutral current from electron neutrino. And here is a neon track. And this is a new tau that you have a double cascade. But let's see that this is one of the most important results from ice cube, which is the measurement of this flavor astrophysical neutrino flavor composition. And this triangle is going to be read like this. So in that point, I have 100% mu neutrino. In that point, I'm going to have 100% electron neutrino, mu neutrino, sorry, is above. And sorry, and this one, 100% tau neutrino. So this is in order to understand. No? You can revise, of course, later carefully. So if you have 1/3 for each flavor, you are going to have the point here. So this is in order to understand. And here is the regions from ice cube, which are very, very spread. And this is the astrophysical neutrino spectra that they have measured. And they can differentiate, or they differentiate from the atmospheric background. And this is the origin astrophysical, this data. And also, well, this is the way that you shape this kind of physics that what happened with this power law, the dependencies. Okay, and finally, well, there are a couple of slides that you can revise later. But finally, which is probably the most exciting result, in my opinion, is that they can measure, they can identify a single source emitting neutrino, which is a pretty amazing result. And this is what we have seen very recently in science in 2022, that they have be able to identify a single source, which is expressed in this plot that combines or mark or use the square angular distance between the force and NGC 1068 and the event direction of neutrinos, and they can identify clearly that this is a source emitting neutrinos, a galaxy, no? So, well, let's finish here. It's fine. Thank you. Thank you very much.
Thank you. Thanks, Alberto, for covering this whole spectrum of neutrino physics. Yeah, now the question.
Sir, so my question is, there are several disagreements in sterile neutrino experimental results from different parts. So there are like large uncertainties in neutrino nucleon cross sections, and the beam flux is uncertainty is also high. So is it possible that these disagreements are because of uncertainty?
Okay. Well, this is very interesting that you pointed out. Unfortunately, I didn't have the time to talk about, for instance, Minerva, but you have pointed out something very interesting, that we actually, one of the major problems in terms of uncertainty for neutrinos, I didn't talk about that, unfortunately, is the neutrino cross-section. I show you only the neutrino cross-section, but the major problem in terms of uncertainties, in fact, you can revise a recent paper discussing this kind of uncertainty for oscillation parameter, is the neutrino cross-section. Well, I haven't heard really that this could be possible. I guess it's outside the range of error that can, but this is a very good point. No? What I would say is the following: suddenly we can, as a theoretician, thinking that probably if we modify the neutrino cross-section in somehow, probably we can explain, I mean, in the opposite way, no? But in principle, for the regular ones, there is no problem for the standard ones.
I was wondering if there are any assumptions under which we can say that sterile neutrinos could be dark matter candidates.
Can you repeat?
Are there any assumptions under which we can say that sterile neutrinos could be dark matter candidates?
Dark matter candidate?
Yes.
Dark matter? Well, I don't know if it's possible, because the mass is too light to get clamped. I am not sure. I'm not sure what I'm saying is if there are other possibilities that can match with that. So I would like not to give you a wrong answer, but as long as I understand, if you have a very light mass, you are not going to clamp to get matter. So you need some kind of higher mass. I don't know if 1AB can explain that. I don't recall exactly if I can explain that, but thank you for the question.
Thank you.
Sorry for not giving you a full answer.
We have to stop here.
Oh, thank you.
This is the large collection of the institutes.
Thank you very much. Thank you.
And so also a small painting.
Please, the photo. I want the photo. Huh?
Yeah, here's the painting of the local tribal people.
Send it right now, please.
Yeah.